What we're going to take a look at here is taking these ideas from a few previous videos of being able to encode reputation inside of the mathematics of game theory through repeated games to understand how altruistic behavior can emerge. And what we're going to use is this game here. This game is called the Prisoner's Dilemma. It's its most basic or most traditional form, I should say. And there are two players. The game is symmetric, so in other words, it's the same from both players' point of view. And there are two actions. The first action corresponds to being altruistic, and the second action corresponds to being selfish. And so essentially they're saying when any two people interact, they can interact in their own self-interest by being selfish, or they can act in the interest of the others by being altruistic. And so if both players are altruistic, we're in the first row and the first column, both players get a 3. If both players are selfish, we're in the second row and the second column, both players get a 1. If one player is altruistic and the other player is selfish, the altruistic player gets a 0 and the selfish player gets a 5. So in other words, the selfish player takes advantage of the altruistic player. And if we look at this game and we say, what is the best response to the first column? So what is the best response to being to someone being altruistic? Well, it's to be selfish. And what's the best response to someone being selfish? Well, it's to be selfish. And so what we get is a Nash equilibria where both players act selfishly. And so by itself, this little game, essentially the story ends there. And in any given interaction between two individuals, this basic game suggests we should all just act selfishly. But that's not what happens, right? In real life, around us, we all act relatively altruistically. We all work together. And so this game, the Prisoner's Dilemma, is a model that allows us to model that. In the traditional version of the Prisoner's Dilemma, the actions are not to act altruistically or to act selfishly. They are called cooperation and defection, and the story is about two prisoners who are caught and can either spill the beans on each other or not. But in a way that's irrelevant. The important part is this is a model of basic interaction where you can either act in your self-interest or in a group self-interest. And so where this game becomes immediately interesting is if you make it a repeated game with however many stages. So if we just look at the case of our stage, a two-stage repeated game, then all our possible histories are, well, no one has done anything yet, and both players have acted altruistically. The first player has acted altruistically, and the second player selfishly. The first player acted selfishly, the first player altruistically, and so on and so on. R2 and C2, I think, is the only one I got missing there. And so those are our histories in the two-stage repeated game. And so strategies for this game will be mappings from this set to actions. Okay, and so if we take a look at one of a few of these strategies, that's perhaps a bit small. Let me make that a bit bigger. If we have to be altruistic unconditionally, so unconditional altruism, and you'll see me sometimes referring to that as cooperation. Unconditional altruism would be written down as, well, every element of that set, phi phi, R1, C1, R1, C2, R2, C1, and R2, C2, all of those would get mapped to R1. So that means always act altruistically. Unconditional selfishness would be replacing all these with 2s. Okay, and that would be unconditional selfish behavior. Okay, but what we can do is also encode slightly more interesting behaviors, if I just make this a tad bit bigger, and not unconditional altruism, but if we consider the strategy that starts by cooperating and then just repeats what the other opponent did. Well, that starts by cooperating. We're doing that, and then repeats what the opponent did. That's that. And then we've also got this one here. So those two are right. But these ones, however, would have to change. So that will become an R2, and that will become an R2. So in other words, I'm going to start by cooperating, and if you cooperate, I'll cooperate with you. But if you defect, if you act selfishly, then I will act selfishly going forward. And this is just some of the strategies, right? Just in the t equals 2 stage game that we're considering here, we have for each one of these choices, we have 2. So we have 2 to the power 5 possible strategies. We have a huge strategy set. And what we can do is study this in an evolutionary sense. And I'm skipping over the basics of that because we'll see that in a future set of videos where we talk about the replicator dynamics equation. But if we write down all 2 to the power 5 strategies and see how they all do against each other, we can actually take a look at what happens. I just pasted this graphic in. We can take a look at what happens if they were to be allowed to evolve together. And we'll see the mathematics about this in the future. But here are some of the strategies that play against each other. And you can see that a few of them have kind of taken over the population. But the interesting thing is the average per turn utility. So we see that we started off and the average utility of everyone in the population was above 2. But as this particular set of strategies have taken over the population, our average utility is 1. And if you remember, an average utility of 1 means that everyone is essentially acting selfishly. So these particular strategies in the overall t equals 2 iterated prisoner's dilemma, cooperation does not evolve. But what we're going to see is as we make t bigger, we get good news. And game theory can be used to understand how altruistic behavior can emerge from complex systems.